Hey everybody, and welcome back to Algebra 2 Online. So the plan for today is to just talk about one important part of rational functions, which is horizontal asymptotes. So to start off, I just want to sketch one of these rational functions that we saw last time. So sometimes you'll run into something like this, and it looks kind of like a more scary rational function than we saw, but if you ever have the same factor on top and bottom, you actually can just like cancel it like that, and you get 1 over x plus 2. And then 1 over x plus 2 we can know as like taking 1 over x right here, and then the plus 2 just acts as like a shift to the left 2. So we would basically just move this vertical asymptote over here to -2. The horizontal one would stay put, and so we would get this kind of graph in yellow here. So that yellow one would be 1 over x plus 2. You'll actually learn in the next video something weird is actually happening when you factor maybe top and bottom and there's a common factor. You actually end up with another kind of like discontinuity. So it's something called a removable discontinuity, but we'll talk about that in the other video. But for right now, if you run into something like this, you can think about just canceling that and just think of it as 1 over x plus 2. And then the sketch would honestly look almost exactly like this. There's actually just one little issue with what I drew, but for right now, that is perfectly okay. So the plan for today is to talk about these horizontal asymptotes that we've been seeing. There's actually a very easy kind of mathematical way to find them. But it actually involves a little bit of really calculus, or maybe pre-calc, depending on how your pre-calc class is. But the thing that I kind of have to teach you about is something called a limit. So in order to know what a function is doing, like way, way, way out at infinity, the formal way to do this is to take this thing called a limit of the function. So if I can do this in two directions too, right? So I can basically check the output of the function out at infinity, and what this is saying is if it approaches some number L, and it also approaches that number L as you approach -infinity, then, so the function value approaches that, then the horizontal asymptote would be that number L. So like in this last problem, as you go out to infinity, you get close to 0, and as you go out to -infinity, you get close to 0. That's actually something in math called a limit problem. And the limit of the function as you go out to 0 is the same as the limit as you go to -infinity, so the horizontal asymptote in this problem is 0. This was actually... There's quite a bit to say, and I don't want to get into too much of it, but this thing over here and this thing over here are kind of the two classic uses of a limit in calculus. And if you keep taking math classes, you'll learn about something called an integral, and that's what this thing is, and it involves a limit. And then this is something called a derivative, and that also involves a limit. But we don't really need to learn about those. I just wanted to show you what some stuff kind of coming up could look like in math. For us, we really only need to know how to find limits at infinity or -infinity. But I thought it might be good, if we're talking about limits, to show like a little bit of some other stuff we can do with it. So I wanted to kind of talk through this picture right here. So in this picture, I can say, so with this hole there, I've got a undefined spot at 2. But literally it's just at 2. It kind of should be equal to 4, but it doesn't. But the curve kind of comes in, and it gets really, really, really close to 4 on either side, whether you come in from the left or come in from the right. And we can actually write this with limits. We can say, we can write down this. We can say limit as x approaches 2. And the way we write that it approaches from the right is actually do a plus sign kind of on the right of the number 2. And then we're taking the limit of the function, f of x. And if what this is saying is, what does the graph approach the output value of it as you get close to 2 from the right? And we can see that it should be 4, right? And then we can also talk about this kind of arrow that I have drawn here. And I can say the limit as x approaches 2, but from the left this time. And I would do that with a little minus sign of f of x. And that also equals 4, right? And so I do think if we're talking about limits, it's good to like show some of these other ones too. And you'll do more of this in pre-calc and quite a bit more of it in calculus. But these are actually also things that you can do with limits. You can like analyze the function value just from one direction or the other. It doesn't have to just be this kind of idea at infinity or negative infinity. All right, so for this problem, I just wanted to show you kind of how we can use limits to start drawing a picture of a graph, which I think will help kind of make some sense of what this limit thing is saying. So, and actually some of these too, actually no, just one of them, sorry. This fifth bullet point here just says, this is truly just a point. It says that at 2, if you plug in 2 the function, you get 1. So we can even just plug that in right now. So let me tick off a few points here. All right, so at 2 we get 1, all right? But the rest of these are like limit things, and so I'll just kind of go through and read them and kind of talk about what it means in the picture. So this first one is saying, as you approach, so the limit as x approaches negative 2 of f of x is 1. So that means that as you get close to negative 2 in the x, right, over here, it's saying that the function value is basically 1. So it doesn't mean that it necessarily needs to be 1. It just means that as you come in, you know, it might do something like that picture on the last slide, where you get something like that. You're just getting really, 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 really close to an output of 1 as you come into that point negative 2. Okay? This one says as you approach 0, the function value like skyrockets down, I guess, to negative infinity. So really this part that I had, I'm actually going to switch it around. So now we know that as we get really, really close to the y-axis, the function value is shooting down to negative infinity. And it must be doing that on the other side too, because it didn't have the like little plus and minuses that these two have for the left and right thing. So we also know that the function value is like somewhere down there. Well, here, let me kind of just give myself a little more room there. So we know it's shooting down kind of on either side of the y-axis. Then this one is one of these, so we call this, this is a limit from the left because it's the negative. So it's saying as you approach 2 from, this was 2. So as you approach 2 from the left, it's saying that the function value is like 0. So as we come into 2, right, we can see that we're getting, I'm just showing it, we get close to 0. But it can't be filled in because we know at 2, the output is 1. So that's why I filled in that dot earlier. Then it's saying as you approach 2 from the right now, that's what that plus means, the function value is 2. So we're getting close to 2 up there as we come in from the right. And then as we go out to infinity, out here, right, it's saying that this is really, which one is like, this is the most like connected to a horizontal asymptote, which is really the one that we're going to use mostly. But it's saying that the rational function here is approaching 1 as you go way, way, way out to infinity. So it's doing something kind of like that. Right? This is like some sort of weird rational function. I don't know what the equation of it would be. There's a few right answers here because this first one that I did, where I said as you approach negative 2, it equals 1, the limit, it also could be filled in there. It doesn't need to be open. It's just saying that the output is getting really close to 1, but it doesn't necessarily need to be 1, but it could be 1, right? So that could be drawn that way as well, and that would still be correct. But then the second one is y, it's shooting down, right? Because as you approach 0, it's going to negative infinity. And then this one is saying as you approach 2 from the left, you're getting 0. As you approach 2 from the right, you're getting 2. And then f of 2 is 1 right there. That's where we actually fill in the circle. And then this is like the horizontal asymptote thing. As we approach infinity, we shoot way out, we're getting an output of 1. And that really is, like this sort of imaginary horizontal line that we're getting really, really, really close to. So what I want to do now is just kind of sell you on why the horizontal asymptotes for x, 1 over x to the n, for any power of n, really would just be 0. So it's easiest done with, honestly, just some numbers. If we, so I'll put the graph up here again. So for 1 over x, like this, we do know that there's this horizontal asymptote here, right? And you can really think about it just with, if you think about some numbers. So as you plug in larger and larger x values, right? You know, 1 over 10, 1 over 100, 1 over 1,000, let's do one more, 1 over 10,000. You can see that these numbers are just going to get smaller and smaller and smaller, right? And that's what it means to say that the limit as x goes to infinity of 1 over x is 0. And you do the same thing if you plug in larger and larger negative numbers, right? You'd have 1 over negative 10, 1 over negative 100, 1 over negative 1,000, and so on. But, those are still going to approach 0. It's just approaching 0 from underneath the x-axis rather than above the x-axis. That's why the graph is down there, right? So it still equals 0, but it's just approaching 0 from kind of below rather than above, okay? And no matter what power of x you have, it will always approach 0 if it's in the bottom, right? And the only thing that actually changes is how quickly you approach 0. If you have 1 over x squared, it's going to get you to smaller numbers quicker than 1 over x, because you'll square all these numbers, this 10, this 100, this 1,000, and so on. And so the numbers get a lot smaller because you're doing 1 over a bigger number. And same thing, if you just do 1 over x cubed or 1 over x to the 4th, the only thing that's changing is how quickly you get to 0. And the bigger that number is, the quicker you'll get there. So what I want to do now is show you how, given a much more messy looking rational function, we can actually find the equation of the horizontal asymptote. So it basically just builds off of what we just talked about, that if you have 1 over x to any power, the limit as that thing goes to, x goes to infinity there, is going to always be 0. So we basically we get that into the problem. And we do it this way. So first, just identify the largest exponent in the rational function. So in this one, it's going to be 3. And then what you'll do is you'll just divide every term by that power, like x to that power. So we're not going to change it that way, because if we just do it something on top and bottom, right? Like if I divide by x cubed on top and bottom, don't have enough room there. It's basically like multiplying by 1, so that's okay to do. So then I would get this. All right, so all I did there was I'm just dividing every single term by x to the highest power I saw in it, which was 3 here. And then I've simplified it. This would be simplified to 1. This is canceling 1x, and you'll get 2 over x squared. This is just staying put as 1 over x cubed, and so on. And then, so that's kind of steps 2 and 3 here. And then basically we're just going to use this 1 over x to the n limit idea to evaluate like everything in here. So one of the nice things about a limit is that you can actually just take I'll have to erase this here, but the limit of like x as you approach anything of like f of x plus g of x is actually the limit of each thing in here. So you can just basically apply the limit to individual terms, which is the nice thing that we'll use. So that's something that you'll learn about in a calc class or a pre-calc class. They'll talk about these limit properties, and that's like a really nice one that we can just use. So we can basically just do the limit as x goes to infinity of every single thing in here. And what's really nice is any of the ones that are like 1 over x to some power, those ones should just all cancel off and give you 0, right? Because the top, like if you take this one, the top's always going to stay 2, but if you do 2 divided by larger and larger and larger numbers, then it's always going to still go to 0 eventually. 9 divided by x cubed is going to go to 0 really quick, because when you cube larger and larger numbers, it gets really, really big. So you're doing 9 over like huge numbers, which is super small overall, right? So once you take the limit of like every single term in here, this part just stays constant. The limit of 1 is just 1, because if you have just a constant 1 horizontal line like that, as you go out here to infinity, it's just going to always be 1, so that's never going to change. So basically, after all that, you just get this thing simplify into like 1 plus 0 plus 0 over 4 minus 0 plus 0, or just a quarter. And this thing that you get left over, this is what your horizontal asymptote is. Y equals 1/4 for this is the, output value that this rational function is approaching as you go out to infinity. And you can see it. This is the picture of the actual function, and that dotted line is actually 1/4. And you can see that it actually does get really, really close to that as you go out to infinity. And one thing that I should add here, so if I go back to the definition of these horizontal asymptotes, I said that the horizontal asymptote is going to be this thing L that you get when you do the limit out as x goes to infinity, or negative infinity. So I did, because it's or, I could have done the whole problem with, here we go. I could have done the whole problem with as x goes to negative infinity, but it really doesn't change anything, right? Because you would have just done like, for this one, it literally won't change it because the squared on the bottom, so the negative would become positive anyways. But that one right there, being x cubed, you would still get 0 because it's 1 over a really, really large negative number. It's like this thing that I was talking about. It's still going to get you 0. So that's why in the definition, you'll see the word or being used. It doesn't really matter if you check the limit out at infinity or negative infinity. It's going to be the same thing. I typically just do infinity because then it's less to write. I don't have to worry about the negative there. So I just want to do another example, same kind of thing, just going through it for a different problem. So largest power here is x to the power 2. And I'm basically going to just divide everything here by that, which won't change the overall expression value, right? So if I do 5x squared divided by x squared, that would just be 5. And then x divided by x squared would be 1 over x. And then negative 2 divided by x squared is just going to be negative 2 over x squared. And then we'll have a 1 over x squared in the bottom, minus 4 over x, right? Because if I divide x by x squared, you're going to cancel one of them. And then the last one would just be 3, because I divided x squared by x squared there. So this is just divide every term by x squared, and you get that. And then you can do the thing where you're basically just taking the limit of every single term, which is a nice property of limits. So the limit of 5 is literally just 5. the limit of 1 over x as you go up to infinity is going to be 0. And then any of these that have an x on the bottom of any power is going to be 0. Whoops. There we go. So that's 0, that's 0, and then that would be 3. And the constants will always just stay the same because, you are just drawing a horizontal line, and you're just thinking, like, out at infinity, you still equal that horizontal line. And so we get 5/3. And so the horizontal asymptote in this thing would just be y equals 5/3. And you should, I'm not going to do it here, but you should go plug this thing into Desmos, and you would see that actually, as you go out to infinity, this thing approaches 5/3, the horizontal line 5/3. So, one other thing to note, actually, I didn't bring up in the last problem, but so vertical asymptotes are, you can never cross them. They're literally just spots where it's undefined. So you can never ever cross this point right here. It's just undefined there. Horizontal asymptotes you actually can cross over. So there's some graphs out there where they do some really weird things where they cross over the horizontal asymptote like a bunch of times, but then they still approach it in the end. So like what I mean by that is something like this. So there's a very famous graph that looks like it kind of oscillates back and forth over the x-axis, but then approaches it and gets like really, really close on either side like that. You should kind of think like some sort of like signal kind of wave sort of thing like that. But the x-axis is like an asymptote here, a horizontal asymptote, and you can cross those. You can never cross vertical asymptotes. So just write that up here. Can cross horizontal asymptote, but cannot cross vertical asymptote. You'll see that in some graphs, like this one. So here it crosses over it, but then we still approach the 1/4, but you'll never cross that because that's just literally a spot where it's undefined. All right, so I just want to do one more problem, and it's kind of a weird one. This one is definitely harder than ones that I'll expect you to do. You're going to have ones much more just like this one for finding horizontal asymptotes. But it is actually possible. So if you graph this, you actually get this. And you can sort of see that there's a horizontal asymptote here at 1. And then there's actually a horizontal asymptote here at -1. And you can actually get this. You can get like multiple horizontal asymptotes popping up in a problem. And it actually ties in nicely with our last unit, so I wanted to go through this one. So you can do this one of two ways. I'm going to start by just simplifying this thing. So what I'm going to do is I'm going to take x squared out of the top, okay? And if we do that, we would have 9 and then plus 2 over x, right? Minus 5 over x squared. And then I'm going to divide by, so I just like factored that out, I guess. So we'll just leave that there for right now. So that is just factored out, right? Then if I was to take the limit of this thing as x goes to infinity, let's say, any of these ones that are like 2 over a variable or 5 over a variable, those are going to go to 0, right? So really this could be simplified even further to 9 x squared over 3x. And then we know that from our last unit, if you have square root of x squared, that's going to be absolute value of x. So this is like 3 absolute value of x over 3x, and then those would cancel. And so you're getting, after all that, something that's much simpler, which is just absolute value of x over x, okay? And this is why you're actually going to get 2 answers. So you also need to remember what absolute value looks like. Absolute value, right, just looks kind of like this, that kind of V thing. And so if we did the limit as x goes to, let's say, positive infinity of absolute value of x over x, which should be the same limit as this problem because it just simplifies the same way, right? then we know on absolute value of x, as we go out to the right, we get x. So this is the same as the limit as x goes to infinity of x over x, which would cancel, and you'd get 1. And that's why, as you go out to the right, you're getting 1 as a horizontal asymptote. If you do the other side, if you do the limit as x goes to negative infinity of absolute value of x over x, now, as you go out to the left in absolute value, right, you would get negative x, right? That's what that piece is right there. And then those would cancel and you get negative 1. So sometimes when you have these square roots in problems, like in rational functions, you get, you really get it actually when you do square roots of an x squared in there. There's going to be absolute value of x popping up, right? And because of that part popping up, that's from our last unit, really important little part, you get 2 different things like this. So this one's definitely tricky, but I wanted to show you it just because I think it's a good one to see. A lot of them will be like this, though. This is kind of a more standard one.